Hello. Okay. All right. My bad. Because I haven't done this for a while, but this should not happen. So microphone now, I think is back. Okay. Um, this is really bad. So I have been talking for 20 minutes, but nobody can hear anything about what I talk about. But luckily today is a special session, so hopefully you can figure out what I'm trying to say here, okay? So today we are talking about the need of everyone to get exposed to competition math, no matter what you want to do in the future. Even say, I'm not that interested in math, and I don't really want to have some bragging right about my mathematical capacity, or I don't need this for my college application. You still want to get exposed to competition math. And the reason is right here. Competition math, number one, will make you smarter. Okay? That's truly important because competition math, unlike school math, we will learn things, solve problems in a way that genuinely stimulate your thinking. How we understand a problem, how to solve a problem. And usually you will see problems that you never saw in school math. And the problem solving process could be very different as well. So that really help you to become a better thinker and a better problem solver. This kind of skill is not limited to math. It can be applied in many different contexts. So how to solve a problem is absolutely a skill that you want to learn even without being limited to a mathematical framework. In reality, anything you will have to do in real work, in your future work, is more or less a problem solving process. Okay, whether you want to do business, whether you want to become just a public figure like a politicians, you'll face all kinds of problems, and how to solve them actually share a common subset, and that you can actually learn a lot from a mathematical problem solving. Well, in school math, we teach you some very mechanical way of solving a problem. You memorize a lot of things. You learn a lot of rules. And when you see a problem that was presented to you before, that you solved before, you know what rules and what procedures to apply to solve that problem. So it's kind of just a training that help you to solve a certain specific problems. And competition math is very different from that you usually will be given some unseen or unfamiliar problems. You are supposed to figure out a way using the basic knowledge that you have to solve those problems. And the process is really sometimes, you will learn quite some new tricks, new procedures. That's part of it. Nobody can get around that. But more importantly, it's more like using a familiar tool or familiar tools in some unexpected ways. You know how to use a hammer to just hammer a nail, but can you use that hammer for some other things that you never thought before? Maybe that's not a perfect analogy, but that's what we want to do. So using your skills to solve some kind of never solved before or unfamiliar problems. That's a huge goal for you to do competition math. And the second reason for you want to do competition math is that because competition math involves many different areas of math. Before we fix the microphone issue, we say that in school math, you from K-12, you generally only do through those things, right? You do arithmetic, then starting perhaps right now, you will do some algebra, and eventually in junior or senior years in high school, you will do a little bit calculus, and you are supposed to do some geometry. But that's about it in K-12 education. But in competition math, we will do algebra, we will do geometry, we will do number theory, and counting and probability. Those are the four major subjects you will encounter in competition math in middle school and high school. But very often, you will see a lot of problems that actually mix those subjects together. Sometimes two of them, sometimes even three or four of them. Or those subjects will get involved in one single problem. That's both challenging and exciting. It really just examine you how to apply your knowledge to just solve a problem all at once. You will have to use your skills to think from many different angles to attack a problem. So this really just broadens your mathematical capacity. So the point here is that for competition math, you will learn a skill that help you solve some unfamiliar problems. Problems that you were not taught how to solve before. That's a hugely important skill. Along the way, it will stimulate your intellectual just smart, your capacity to think very deep into the nature of problem. It's really an intellectual challenge, okay? It's fun. And in very real sense, it makes you smarter. And number two important reason is that it will be eye-opener for you when you see a problem that requires you to apply all your skills, not just one specific area of skills. When you combine all of them into a single problem, it will really be eye-opening. It will broaden your understanding of mathematics as a whole. Because all those areas can actually be intertwined and they interact with each other to in one single problem. It really helps you to have a much more profound understanding of mathematics. Why is that important? Because if you continue to receive higher education, learn more math, more engineering, more sciences, this kind of deeper understanding of the subject will help you to learn those just higher education contents much more easily, okay? Because you're much more better prepared to face the future challenge in that sense. So if those are not enough for you to get interested in competition math, then I have to say you are missing an opportunity here. So even you think that you are just a kind of just a quote unquote average math student at this stage, um, you should be truly encouraged to get involved in competition math. It actually will help you do better in school math. Because as compared to competition math problem, school math problem tend to be less stimulating, much more mechanical. And once you, just like if you play basketball, if you are forced to play with taller, stronger kids, while you may struggle on a team where most of the kids are older, taller, stronger than you, you may struggle quite a bit there. But if you manage to survive somehow and then go back to your regular team, playing with kids, just kind of at your age, about the same height, same weight as you, you will see that you will have a huge advantage there because you are used to a much tougher environment. So when you are back to normal, you will feel, while you actually not, you will feel you are taller, you are stronger, and all that. So even if you do not really think that you are a strong mathematical student for now, I highly encourage you and actually urge you to get exposed to competition math. So let's talk about more specifically about those subjects. And maybe we should have a clearer picture of what competition math is in America. So let's talk about the roadmap, the most well-known competition math in America. So competition math in high school, the crown of the jewel, the ultimate thing, just like the World Cup, we are World Cup games we are watching right now, right? You should know that soccer is number one sport in the whole world. Well, it's not that popular here in America, but it's holy religion in Europe and South America and in many other places. So soccer is the most popular number one sport in the world. And what is the most important trophy in soccer? That's the World Cup. Every 4 years. It's just like a big festival, but it's also like a world war. All countries want to perform well in the World Cup soccer tournament. But every 4 years, only 32 teams can be qualified to go to the tournament. So in competition math, the ultimate goal is what we call IMO. It stands for International Mathematics Olympia. So this is the World Cup in high school competition math. It's international math Olympia, right? So every country will send a team consisting of 6 students. 6. That's it. 6 students go to the IMO to compete. So America, of course, is no exception. Only 6 students every year can make the cut to be part of the United States Math Olympia team to compete in the IMO. So how are those students selected? Well, usually there is a mob. This is just it's a summer camp every year, about a few dozens. So around, say, in the old days, only 30, now expanded, but still The absolute number fluctuates from year to year, but that's just in general, about 50 or 60 students every year in the summer can go to this camp to receive training, and then from there will be a team selection process every year to decide which 6 students will represent the United States and go to the IMO. But how do you qualify for this MOP? Well, there will be a series of mass competition exams that you have to go through. So there's an AMO, and there's a JMO, which represents the Junior Mass Olympiad. So AMO is just a United States American Mass Olympiad. Well, JMO is a kind of similar concept, but it's limited to up to grade 10. That's why we have a J here. It's a junior. So J represents junior. JMO, this is just American. This is up to grade 12, and this is up to grade 10. So those are 2 Olympiad level math competitions each year. So in order to qualify for MOP, you have to perform really well in either AMO or JMO math competition every year. But how many people can make, say, AMO to get qualified to participate in this math competition? It's about somewhere around, say, 230 students. How many students can qualify for JMO? It's about 270 students. Those numbers are rough numbers. They fluctuate from year to year. But the general rules is that the Mathematical Association of America, which is the professional mathematician organization in charge of organizing those competitions, they try to manage the total to be around 500 students, high school students every year, can qualify for those 2 competitions. So AMO is up to every student up to grade 12, but in reality, because the IMO occurred at the latest in your grade 12, so in order to qualify MOP, you will have to go 1 year before that, right? If you're already in grade 12, you graduated. So there's no point to go there. Next year, you are supposed to go to college. So the very latest you want to be just in that MOP camp, that will be the summer after your grade 11. So AMO and the JMO are the 2 math competitions which allow you or qualifies you to go to MOP. And JMO in general try to select those younger students who have the potential to do even better when they grow older. So this is limited to grade 10, and JMO has virtually no age or grade limitation. So there are only about 500 students who can actually even just participate in those 2 math competitions every year. Then who will get the qualification? Well, before that, there will be the AIME, which in general is a selection competition math. This is called math examination, okay? And I stand for invitational. So even this math competition, every year a few thousand students. In recent years, they changed the rule to, in general, allow more students to participate in this. But overall, still, let's just have a very rough ballpark number. Let's just say every year, only about 5,000 students can go to this invitational, by invitation only, math competition exam. So This is a qualification math competition for both AMO and JMO. Okay, but this exam alone does not decide whether you can go to either JMO and AMO. Okay, because like we said, there are only about 5,000 students can participate in this invitation-only math competition. So who get invited? So that will be through even just further qualification competition. That's the AMC 10 and 12. Okay, as you can see, 12 means that this exam is limited to any student up to grade 12, while AMC 10 is limited to student up to grade 10. So AMC 12 actually correspond to is a part of the qualification exam for AMO, while AMC 10 is the corresponding qualification exam for JMO. So the rule is like this. In order to qualify for AIME, you have to go through either AMC 10 or AMC 12. So AMC 10 or 12 is serving as a qualification examination for AIME. Okay? And the rule for AMO is that you will be evaluated based on both your AMC 12, AMC 12 plus the AIME result. Those two exams combined together determines whether you can qualify for AMO. Similarly, AMC 10 plus AIME, those two combined, the two scores combined to determine whether you can qualify for JMO. Okay, so long story short, AIME is a qualification competition for both AMO and JMO. But to qualify for AIME, you will do either AMC 10 or AMC 12. So those two exams are qualification exams for AIME. However, AMC 10 or 12 will be combined with AIME results to determine whether a student will be ultimately qualified for either AMO or JMO. Okay, so the true math competition starts at the AMC 10 and 12 level. So up to grade 10, everybody can participate in AMC 10. And upgrade to grade 12, everybody can participate in AMC 12, but there's no lower bound. Even if you are grade 6 or 7, you can do both AMC 10 or 12. It depends on what your choice is. Of course, AMC 12 will be harder than AMC 10 because the subject will cover more advanced materials because there are 2 years, 2 grades apart, at least in theory. So those are the typical high school math competition. So if you are in middle school, you will also have AMC 8. That's one thing. And another called math count. Those two are typically for middle school students. You can see that the AMCA is very similar in concept to AMC 10 or 12, but AMCA is not a qualification exam. That means that you don't need to pass the AMCA to get qualified to participate in AMC 10 or 12. Anybody can, even right now, if you want, as a 5th grader, you can try AMC 10 or 12. The only issue is that probably you will not be able to do many problems at all if you have not learned most of those materials. So MCA is actually an independent exam. It's just for fun for middle school students. It's not part of a qualification process for anything. And then you have math counts. Many of you, actually, I have a math counts a training program. So math counts really, it's just for middle school students in grade 6 through 8. Okay, only those 3 grades of students can participate in math counts. Math counts, the format and the content of math counts are close to AMCA. So the two are not the same, but they can serve each other well. So if you train for math counts, it will certainly help you to do AMCA or even AMC 10. And vice versa. If you prepare for the AMC series of math competition and you are in middle school, it will certainly help you to get better scores in math count competition. So those are the roadmap for you if you want to do competition math. Okay? So, but let's now talk about a little bit about, so what exactly you will do in those 4 big areas: algebra, geometry, number theory, and accounting probability. What are those subjects about? So let's talk about something that you perhaps already have some exposure: geometry. So what is geometry all about? Well, very unfortunately in America, in school math, the geometry you will study is very much a severely watered down version of geometry. Geometry has a long history in our human being knowledge accumulation. It actually appeared about 2,000 years before algebra was even born. So the ancient Greeks, those great Greek mathematicians, more than 2,000 years ago, studied geometry. And that culminated in the most published textbooks of all time, which is called Elements. Okay? That, I think it's Element. Okay? So that was written by a mathematician in ancient Greece called Euclid. So Element not just contain geometry, but also some number theory stuff. But really, that's a just wonderful masterpiece, not just in math, in all scientific subjects, perhaps in all subjects. So it was one of the most important a book that was ever written in our human history. But what does geometry do? Well, geometry in general is the study of figures, but there are a lot of underlying connection with other branches of mathematics. So let's just give you a very simple example. Everybody knows what a triangle is, right? Let me give you a triangle. Okay? We know a triangle is characterized by 3 sides and correspondingly 3 vertices. So if I specify those 3 vertices which are not on the same line, if you have 3 points which is on the same straight line, then you don't have a triangle, right? So the only condition is that those 3 vertices cannot be on the same line. If I have 3 points not on the same line, then I will be able to connect those 3 points pairwise. And each, you can see that with 3, you have 3 pairs. Why you have 3 pairs? That's actually a counting problem, but we will talk about that a little bit later today. So once you have those 3 points, you will be able to connect them pairwise. You have 3 pairs, therefore you have 3 sides. So then you can see that you have a triangle. Okay? So geometry is the study of geometric figures like this. And it can go to much more complicated than this. But let me ask you a very specific question. What is the possible relationship among those 3 sides? Well, you have 3 sides. We know they have lengths. Some side could be longer or shorter or equal to other sides, right? So how many situations we have here? Well, we can start with the simplest case where we have all the 3 sides are equal. That means that all the 3 sides are of the same length. In that case, we call this a equilateral triangle. That's perhaps the ideal case, right? You have a triangle where all the 3 sides are the same. Okay, in that case, we actually will be able to get a lot of interesting results about this triangle, but this is the most basic case. We call that equilateral, meaning that all the 3 sides are the same. If not all the 3 sides are the same, perhaps 2 of them are equal to each other, but they don't have to be of the same length as the third one, right? In that case, we will have what we call an isosceles triangle. So isosceles triangle is such a triangle that you have 2 sides that are equal to each other. How about the other side? We just don't specify whether the 2 sides will also be equal to the other one. So when they do, actually, an isosceles triangle will degenerate into an equilateral triangle. So in general, that's not the case. So we just have an isosceles triangle. You can go this way as well. So this is a isosceles triangle. It's a weird word. Isosceles, actually, I hate to spell that, so I'm not going to do that because on the computer, I will be much easier to spell that word. But on writing, I don't want to expose my spelling problem. So it's a weird word. So the second case is that we only have 2 sides, or at least have 2 sides that are equal to each other. Now, if that condition is further removed, what do we have? We have a regular triangle where all the 3 sides are different. We actually also have a term for that. It's called scaling triangle, but usually we don't do that. It's just that that's just a triangle. All the 3 sides are different from each other. Now that becomes interesting. So that's just that we have those 3 sides. Because all the 3 sides are different, you can see the 3 angles. They do not look exactly the same, right? But can we say something in the affirmative? Actually, the converse is also interesting. When we have an equilateral triangle, all the 3 sides are equal. Can we tell something about those 3 angles? As it turned out, when you have an equilateral triangle, all the 3 sides are the same. Those 3 angles must be the same. Okay, that's not a coincidence. Similarly, when we have an isosceles triangle, say this side is the same as this side, you can see this is symmetrical, right? There's some symmetry here. By symmetry, we mean if you have a line like this dividing this triangle into 2 quote-unquote equal parts, or identical part, what we really call congruent part, looks like the two triangles can be folded onto each other so that this angle actually is the same as this angle. But can we tell for sure that's the case? Why and why not? Well, that's why you study geometry. But now back to this third case. If all the three sides are not of the same length, so one must be longer than each other, and the three sides actually need to be ordered, right? That's the longest, the shortest, and that's the third one in between the two. So that just say, in this triangle, it seems that AC is longer than AB. This side is longer than this side, as we can tell just by taking a quick look. Can we say something about angles? As it turns out, the angle, this angle, what we call ABC, this angle ABC must be greater than this angle ACB. What this means is that the longer side will face, this is the angle faced by that side. This angle will be larger than the angle faced by the shorter side. So longer side will face larger angle, and vice versa. Shorter side will face a smaller angle. So that means that if we tell you AC, this side is longer than AB, you should be able to conclude this angle ABC, which is faced by AC, will be larger than angle ACB, which is faced by the shorter side. But why? From the figure, we can clearly tell that should be the case. But that's not mathematics. You have to prove, go through a process, what we call proof. Show me if I have a longer side, then the angle faced by it will be necessarily larger than the angle faced by the shorter side. It sounds simple and intuitive, right? But you have to prove it. And that's the most challenging part of mathematics. You have to prove an idea, a conjecture, to prove that what you state, your statement, is actually true or correct. That's what we call a proof. Okay, so geometry actually involves study of many different problems of this type of nature. You have to prove some inherent properties associated with your figure. Okay, so in geometry, you will see that the triangle or polygons are important, but also you have a lot of problems involve circle. And why circle is so important? Because circles are the simplest figure you can get if you have a point and you have a line segment. You can imagine how we draw the circle, right? You rotate that line segment about this center point, you get a circle. This is perhaps the most beautiful geometric figure you can see. And from there, you will learn a lot of beautiful things, and they have profound connection with algebra or some other areas of mathematics. So geometry is perhaps the most interesting subject you will ever study. That's not exaggeration, okay? if you like geometry, you will like math. The converse is true. If you are really a very strong math student, you will like geometry and all those proof-based problems. Okay, so that's geometry. Then let's have because we got 20 minutes just of no talk, so I will extend this a little bit. So let's talk about number theory a little bit. In our free Asian math class, so far we have reviewed basic operations, addition, subtraction, and multiplication. We have not actually talked about division yet. We will soon. But what is number theory? Number theory is primarily about the study of integers, and in a sense, only about positive integers, but negative integers will be included. So it's about integers. Well, if you extend that to the left, we will also have -1, -2, and so on. But primarily we deal with non-negative ones. Let me ask you this question. We already learned addition. If I give you addition as your only operations, now, what do you need? Some smaller building blocks to build all those numbers? Let me repeat, you only have addition as an operation available. You don't have anything else. Then what do you need to build all those numbers? We actually have discussed this, right? You need a 1. And you also need a starting point 0. Once you have 0 and 1, and this operation addition, you will be able to build all those numbers, because from 0 with this operation plus 1, it will give you 1, and from 1 you further plus 1, it will give you 2, and so on. So all you need is an operation addition and a number 1, and then you have a starting point 0. With those things, you can build all those numbers. And this is actually the counting process. Now, if I change this scene, if you only have multiplication available, remember, you only have multiplication available. If I ask you the same question, what do you need to build all those numbers? 1, 2, 3, 4. All those positive integers. What do you need? Well, as it turned out, you need something, and you only need something what we call prime numbers. Well, we have not studied this yet, but let me give you, some of you may have heard of it. Let me give you a very quick introduction what are prime numbers. Well, prime numbers are numbers like 2, 3, 5, 7, 11, 13, and 17, and so on. Why those numbers are called prime numbers? So now you have to look at what we left out. You have 1 is a special one we put there, but 1 is neither prime nor composite. Now from there we leave out 4, 6, 8, 9. 9 should be here. I don't have enough space, but I will write this way. 9, 10, and we leave out 12, 14, 15, 16, and so on. So what is the difference between those numbers in red, what we call prime numbers, and those numbers in green, what we call composite numbers. Well, a prime number can only be written as a multiplication product by two integers, 1 and itself. For example, how can you write 7? It can only be written as 1 times 7, right? 11, only 1 and 11. You don't have any other way to write a prime number into a product, a multiplication. On the other hand, all the non-prime numbers, what we call composite numbers, can do better. For example, let's start with the smallest one, 4. 4, every number can be written as 1 times itself. That's a given, right? 1 times itself. So anything prime number can do, a composite number can do as well. But 4 can also be written as 2 times 2. So this is the big difference. Any number can do better than 1 times itself. That's not a prime number. That's what we call a composite number, because you have more than one basic ways to composite that number. On the other hand, if you can only do this 1 times yourself, that number is a prime number. Okay? So number theory, a huge tool or a huge part of number theory is the study of those prime numbers. Why? Because the prime numbers are the multiplicative building block of all integers. Okay? So what we mean by that is that if I give you all the prime numbers, well, this list is, there are infinitely many prime numbers, 2, 3, 5, 7, 11, 13, 17, next is 19, next would be 23, and so on. The list goes on forever. But very surprisingly, any number, no matter any integers, I should say, positive integers in particular, no matter how big you are, it's made of a product of certain prime numbers. For example, let's say 18. How do we write 18 as the multiplication of prime numbers? Apparently, 18 is 2 times 9, right? 2 times 9. 2 is the smallest prime number, but 9 can be further broken down into 3 times 3. Okay, so 18 can be broken down into a product of multiple basic prime numbers. Well, in this case, we have 2 3s, so 3 will appear twice, but it doesn't matter. The point is that every integer can be broken down into a multiplication of certain prime numbers. Okay? If the number itself is a prime, like 19, of course, the broken down version is just 1 times 19. But that's also a special case because we have 1 here. 1 is not actually considered as prime, but if we remove this 19, just 19. This is also just breakdown. If we understand this is what we mean by multiplication without that 1 times part, this is unified with this. So point is that every integer, no matter how big it is, it will be eventually broken down into a multiplication of all the prime numbers. So because of that, if we only have multiplication as the operation available, then all we need in this case the building blocks will be those prime numbers. We don't need anything else. We can use the multiplication operation and all the prime numbers to build any number. Because the reverse is true. Any number must be broken down into the multiplication of those prime numbers. And this is a very important and very significant result in mathematics, what we call the fundamental. Look, when you talk about something fundamental, that must be super important. That's called the fundamental theorem of arithmetic. And this was first proven by Carl Gauss. Okay, so this theorem says that every number has a unique breakdown into multiplication of prime numbers. And number theory has everything to do with the study of prime numbers. So numbers are truly interesting. And why this is so interesting? Because it gives us some deep understanding of the mathematical world. Everything starts with numbers. Like we said, start with the counting numbers, the natural numbers. And what we mentioned earlier, the communication problem, well, it means that part. In computer networks, we use computer devices, including your smartphones, to do all kinds of communication. A huge problem of that is that how do you know your communication is safe, is secure? Nobody actually can, between you and your remote party, behave like a middleman, change the content of your conversation. When you tell the other side, I spent $500 to buy a new computer, how do you know the other side will not receive a version say, hey, I spent $1,500 to buy a computer? What if someone add that 1 in front of 5? How do we guarantee that such communication is actually secured? Nobody can change it. Nobody can modify it. Nobody can fabricate anything. Well, at this time, we heavily rely on a super important result in number theory, and we use a technique called public key to make sure that our communication is secure. And this public key algorithm has everything to do with number theory. And in general, cryptography is something you will learn how to make the communication secure. And under this technique is number theory. Okay, this is just one example of what we do with number theory. But number theory is hugely important and interesting. Okay, so then we have talked about the geometry and number theory. We're not talking about algebra, because algebra everybody needs to learn it. But algebra is also a very big topic. You will encounter many algebra problems that you will not actually see in school math. We will talk about the counting. We actually have learned a little bit of counting, right? But we also will learn the closely related concept, probability. Okay, so we have already learned natural numbers 1, 2, 3, starting from 0, 0, 1, 2, 3, 4. That's counting. So everybody knows how to count, but quickly you will learn something quite difficult. Okay, so let me give you one simple example and one very challenging example to illustrate what this is all about. So let's just say I give you a big sequence starting from, say, 135. Now I give you 135, 136, 137, all the way, say, until a very large number, 2,584. This is a very long sequence, right? Starting from 135 all the way to this 2,000 some number. Now I ask you this question. How many numbers I have in this sequence? Well, this is the simplest, the basic counting problem. You want to count all of them. But in reality, you don't want to count all of them to get the total, right? What do? Well, you do some trick. You think that, well, how do I count how many numbers here? I don't have a starting point at 1. If I start at 1, 1, 2, 3, 4, all the way to this number, now I know exactly this number in that sequence. But I don't start at 1. I start at 135. What can I do? Well, you do some trick. You just imagine you start as 1, 1, 2, 3, 4, all the way up to 134. Let's just say you start with this sequence starting from 1. When you start there, how many total you have? Of course, you have this number as the total number because you start at very number 1. But now what happened? You start at 135, you actually have removed those numbers from the sequence. How many exactly did you remove? Of course, you remove up to this number, so you actually remove 134. So you start with this many numbers, and you remove this many from your starting sequence. How many you have left? Obviously, you have this many left. And this must be the number of your remaining numbers in the true sequence that was first presented to you, right? In this sequence, the count is this many. Why we are subtracting 134 instead of 135? Because if you subtract 135, you get actually one less because you are subtracting this one too, but you are only supposed to cut off from the number before this number. So effectively, the formula here is that you subtract 135 and then actually add 1 back. So both are the same thing, clearly the same thing, but you will see that you can understand that from this way of thinking, you imagine you have the original sequence and you cut off from there. So you only cut off 134 from the original sequence. If you think this way, it's a little bit different, but it's actually a different thing. So you subtract this one, but you subtract this off, so you have to add it back. Of course, those two versions are essentially the same because 134 is 135 minus 1. Now we know that when we do this, we have to convert this subtracting 1 with the negative sign into it, becomes adding 1. So the two are effectively the same. So this is the simplest counting problem. Okay, but the counting problem can be hugely complicated. Let's just give you one more example. Okay, so let's just say you have bought a bag of bagels. You have bought 12 bagels. And there are 3 different flavors of the bagel. It could be a cheese bagel, an onion bagel, a chocolate bagel. 3 types. And when you bought the 12 bagel, you can choose any of those 3 flavors. Each flavor can be, say, you don't choose that flavor at all. I don't like chocolate, so I don't have any chocolate bagel. But I like onion bagels. I bought all 12 onion bagels. Now the question is that in how many different ways you can actually choose your bag of 12 bagels. Remember, you have 3 different flavors: chocolate, onion, and cheese. For any flavor, you can select up to 12. You can choose just one flavor and leave 0 to the other 2 flavors, or you can choose any numbers in between, like a 3 plus 4 plus 5. Or conversely, 5 plus 4 plus 3. You can choose whatever ways you want to choose. But the question is that in how many different ways? How many different ways? And that is a very classic but very difficult counting problem unless you understand what the trick should be. So, this is a very difficult counting problem. If you don't know the underlying technique, you can see how this actually happened in real life, right? This is a very practical question. You go out to buy a bag of 12 bagels, you have 3 choices. How many different ways you can choose your bag of bagel? And that has everything to do with this area we call counting and probability. If this sounds interesting to you, well then congratulations. You will like math, and in particular competition math. So even if you don't like it now, you can see those problems are actually interesting. If you don't see them interesting yet, I highly suggest you try some problems. Maybe starting with the easier ones. Challenge yourself. Really challenge yourself. That way, you will get into the door of competition math. If you are in 5th grade now, this is the perfect time to start working on some competition math problems. One thing I can assure you is that they look very different from the school math problems that you have already done. Maybe you have repetitively done in many, repeat, but you have never seen some interesting competition math problem. And this is the right time to get exposed to those problems. If you have tried enough, if you don't know how to work it out or work them out at the very beginning, don't get discouraged or scared. You are not alone. Nobody can, without much study, can figure out those more challenging problems upon the first try. So you should make progress if you put in a lot of time to think and attack those problems. Okay? So in conclusion, I want to say competition math is extremely interesting, and it also has many very, very practical meanings for your future study, for your future career. So whether or not you like math yet, you should give them a serious try. That's all I can tell you at this time. Well, thank you for, I know today we don't have many people here. I've been struggling with my voice for a long time. Let's get back to our normal study on this Friday. Okay? Thank you. I will see you on Friday. Bye-bye.